Hello and welcome to tutorial number 8. Our topic today is molar mass, mole ratios, and stoichiometry. Before we get started, just a quick reminder that the notes for each and every tutorial video are available online through my website. Okay, stoichiometry is the branch of chemistry that deals with the quantitative relationship between the reactants and the products in a balanced chemical equation. Well, we already learned in tutorial 7 that it's the coefficients that give us that quantitative relationship in a balanced chemical equation. So we learned in tutorial 7 that we can read an equation. So we'll read this equation here. This equation is written for you on slide 2. We can read this equation as saying 2 atoms of magnesium. And I say atoms because magnesium is an element, so elements are composed of atoms. Okay. So 2 atoms of magnesium react with 1, remember the lack of a coefficient means 1, so with 1 diatomic molecule of oxygen to form, put a little hyphen there, to form 2 formula units of magnesium oxide. And I'm saying formula units here because magnesium oxide is an ionic compound. Remember that your ionic compounds are composed of cations and anions, and the simplest whole number ratio of cations to anions is called a formula unit. So magnesium is elemental, so composed of atoms of magnesium. Oxygen, O2, it's a diatomic molecule, so composed of molecules. And magnesium oxide is an ionic compound, so composed of formula units. Okay, but in truth, atoms, molecules, and formula units are incredibly tiny, way too small for us to see an individual atom or even 2 atoms. Way too small for us to weigh on an analytical balance in the lab. Too small for us to detect. Even if this reaction on this scale occurred right in front of us, we wouldn't detect it at all. This is far too small of a scale. Okay, so let's just think for a minute. How small is an atom of magnesium? Well, we can check the periodic table. Remember that the atomic mass is given for each element in the periodic table. So the atomic mass of magnesium, let's look it up, just grab a periodic table, and I'm going to go out to 2 decimal places here, 24.31, and remember the unit is atomic mass units. Okay, well, we've got 2 atoms, so it's going to be times 2. So we're going to have 48.62 atomic mass units. Let's think about what that is in grams for a second. 48.62 atomic mass units. Let's convert that into grams using dimensional analysis. In every 1 atomic mass unit, there's 1.660539 times 10 to the negative 24 grams. Okay, so pull out your calculator and go ahead and punch that in. 1.660539. Okay. The mass of just 2 magnesium atoms is 8.074 times 10 to the negative 23 grams. Take a minute to think about how small that is. I'm going to write that out of scientific notation. It's going to take me a while because I'm going to need a lot of zeros. 0.000, 000, 000, 000, 000, 000, 000, 000, 0.00000000874 grams. Oh my goodness. Okay, your balance in the lab probably goes out to the centigram, maybe the milligram. So if you were trying to measure out 2 atoms of magnesium, well, not only could you not see them to measure them out in the first place, but your balance would not be able to detect them. So hopefully I've proven to you that atoms, molecules, and formula units is just not a good way to think of our chemical reactions. Instead, we need to think of them in a much larger scale. We think of our chemical reactions in terms of moles. Okay, so I'm going to erase this math that I did down here. Okay, so the mole, spelled M-O-L-E, but abbreviated M-O-L. Okay, maybe you recognize the mole as the SI unit for the amount of a substance. Okay, I'm going to write that here. It's the SI unit for the amount of a substance. And just like a dozen represents a number, a mole represents a number as well. 1 mole is equal to 6.022 times 10 to the 23rd objects. And this number is known as Avogadro's number for the scientist who discovered this. So from now on, when we read our equations, we're going to read them in terms of moles, not molecules, atoms, and formula units. So let's reread this equation here. We can now read this equation as 2 moles of magnesium reacts with 1 mole of oxygen to form 2 moles of magnesium oxide. Okay. All right. And we can get from any balanced chemical equation the relationship between any 2 substances. Okay, so let's just pick the 2 reactants. The relationship between the 2 reactions is a 2-to-1 relationship. We can write that relationship as a mole ratio. So 2 moles of magnesium for every 1 mole of oxygen. Or you could write it reversed, that would be okay too, as 1 mole of oxygen for every 2 moles of magnesium. These ratios are called mole ratios. Okay. And a mole ratio is useful for converting. It's a conversion factor that we can use to convert between the quantity of 2 different substances in a balanced chemical equation. So let's see an example of how we might use a mole ratio in a calculation. Okay, let's erase all of this except the equation. Okay, let's say that we want to react 4 moles of magnesium, and we need to know how many moles of oxygen is that going to take? Okay, well, we can set this up using our mole ratio as our conversion factor to convert between moles of magnesium and moles of oxygen. So let's go ahead and set that one up now. So our given unit needs to cancel out. So we're going to put the 2 moles of magnesium on the bottom, and we're going to put the 1 mole of oxygen on the top so that our desired unit, what we're seeking, does not cancel. Okay, 4 divided by 2 is just going to give us 2 moles of oxygen. You might say, I could have done that in my head, 4 divided by 2, but the numbers aren't always that pretty. Let's say that we wanted to react 0.0481 moles of magnesium. And we want to know how many moles of oxygen is that going to take. Okay, let's set this up. 0.0481 moles of magnesium. And for every 2 moles of magnesium, we know it's going to take 1 mole of oxygen. Okay, so pick up your calculator there. 0.0481 divided by 2. So it's going to be 0.02405. And we'll keep 1, 2, 3. So go ahead and round that off to 0.0241 moles of oxygen. Let's go ahead and circle that. And we'll circle our answer from above too. Okay. All right. So again, the mole ratio is a conversion factor to convert between quantities of 2 different substances in a balanced chemical equation. All right. Let's erase all this and let's go on now to slide number 3. All right. So in the lab, we don't have any piece of equipment that measures in moles. Think about that. When you measure a solid, you typically measure it out based on its mass in grams on a top-loading balance. If you're measuring some sort of liquid, you're probably going to measure it out by its volume and use a graduated cylinder or something like that, probably measure it out in milliliters. Okay, so nothing measures in moles. So it is very important that we are able to convert between moles and grams, something that we can actually measure out in the lab. Okay, so let's write that here. We cannot measure in moles in the lab. So we must have a way, I'll say, to convert between moles of a substance and its mass in grams. And we do. It's called the molar mass of a substance. Write that here, molar mass. The molar mass of a substance is the mass in grams of 1 mole of that substance. Let me write that here. The mass in grams of 1 mole of a substance. And the good news is that it's actually the same numerical value as the atomic mass that's simply given in your periodic table, but instead of expressing it in atomic mass units, we're going to express it in grams, okay? So let me write that here. I'll do a semicolon. It's the same numerical value as the atomic mass, but it's expressed in grams. I'll just put a G there for grams, all right? So let's go ahead and take a minute to look up the molar mass as well as the atomic mass of magnesium. Okay, so for magnesium, Let's first look up the atomic mass. Remember that the atomic mass is the weighted average mass of one atom of the element, and so it's given in a very tiny unit of atomic mass units, the mass of just one single atom, very, very tiny. Okay, so grab your periodic table, look up magnesium. It is a group 2A metal, and I'm going to go ahead and round to the 100th decimal place, so 24.31 atomic mass units. Now that's the mass of just one little teeny tiny magnesium atom. We want to know the molar mass. Okay, what is the molar mass of magnesium? That is, what is the mass of 6.022 times 10 to the 23 atoms of magnesium, this huge quantity of magnesium atoms. Same number, 24.31, but it's in grams. We can measure that in the lab. We can see it. We can detect it. So you can start to see why we think in moles, something much more tangible than a little teeny tiny atom. Okay. All right. So the molar mass, the mass in grams of 1 mole, you'll typically write that also as a conversion factor. So I'm going to write 24.31 grams of magnesium. That's how many grams of magnesium are in 1 mole of magnesium. Okay, so we're going to write it as a conversion factor, and you could flip those as well. You can see where I'm going with this, I hope. All right, before we actually show how I'm going to use that in calculations, let's do a molar mass for a compound. Okay, it's not really that much more difficult, but I certainly do want to show it. So let's do the molar mass for magnesium oxide. The molar mass, it's going to be the mass for 1 mole of magnesium atoms, as well as the mass for 1 mole of oxygen atoms. So we're just going to add them together. So again, go to your periodic table, look it up for each element. So for magnesium, it's 24.31 grams. For oxygen, oxygen is a nonmetal in group 6A, so look it up there. Again, I'm going to round to the 100th decimal place. So I get 16.00 grams. Add those up. You get 40.31 grams. So I can write the molar mass for magnesium oxide as well in this conversion factor form. I'm going to go ahead and do that. So there are 40.31 grams of magnesium oxide in every 1 mole of magnesium oxide. Make sure you are writing the identity of the substance here. You can really start getting confused when we start getting to very long problems. If you're not writing out the identity of the substance, you'll go back and you'll say, wait, that was a molar mass for which one? And then you have to recalculate everything again. So just label it. Just have good note keeping here. Okay. All right, so let's go ahead and take a look at how to use molar mass as a conversion factor. So I'm going to go ahead and leave these numbers up because I think we're going to need those for the calculation, for our sample calculation. So first thing I want to mention when you're using molar mass as a conversion factor is that you are only converting between grams of a substance and the moles of the same substance. Look at that. Moles of magnesium and grams of magnesium. It's the same substance. Okay, so when you're using molar mass as a conversion factor, you're converting between grams and moles of the same substance. All right, so let's say that we were trying to do this reaction and we knew that we needed to use 0.596 moles of magnesium. Okay, and we'd say, well, how many grams is that? Because we can't measure out 0.596 moles of magnesium on the balance. We need to know that in expressed in grams. Okay, so we can use its molar mass as a conversion factor. Put the mole on the bottom so that that given unit will cancel out. Put the grams on the top. so that it will not cancel out, okay? And I'm going to grab my calculator here. So 0.596 times 24.31, we get 14.48876. I'm going to go ahead and round that to 1, 2, 3 digits here. So 14.5, because I'm rounding up here. This is greater than or equal to 5. And my unit is grams of magnesium. So now I can go into the lab and I can measure out 14.5 grams of magnesium for this reaction that I'm trying to do. Couldn't do it when I had it in moles. All right. So let's go ahead and go on to slide 4, which is sort of a nice summary of everything we've been learning today, putting it all together and seeing a nice, concise flow chart for these problems known as stoichiometry. Okay, so we're on slide 4 now. So just a little review here. The only way that we have to quantitatively relate two substances in a balanced chemical equation to one another is through the mole ratio. That's the only way you can do it. Okay, you can't directly relate things grams to grams. It has to be through that mole ratio, which is a nice, easy ratio to get from the coefficients in a balanced chemical equation. Okay. Unfortunately, our balances don't measure in moles, they measure in grams. So you are typically going to need to be able to convert out of moles and into grams. When you do that, you're using the molar mass of a substance and you're converting between grams and moles of the same substance. Don't ever try to use a molar mass to convert between grams of moles of two different substances. It doesn't work that way. Okay, so you'll see a nice flow chart on the bottom of slide 4. I'm going to just sort of copy all that information down up here and we'll create our own flow chart on the board. Now we're going to go ahead and apply it. Let's erase this equation here. Let's go ahead and apply it to a generic equation because the reaction is not always going to be magnesium with oxygen to form magnesium oxide. So let's keep it generic here. So generic reaction. I'm going to write Rx in for reaction. A plus B yields C plus D. Okay, and I think that's the same generic reaction I did in your notes. Okay, so if you want to quantitatively relate, let's say reactant A to product C. You want to know, if I react this many moles of A, how many moles of C am I going to get? You want to do some quantitative relationship there between A and C. The only way you can do it is through the mole ratio. So if you're converting moles of A to moles of C, you must know the mole ratio of A to C. And where do you get that? You get that from the balanced chemical equation. Okay. Since we don't actually measure moles in the lab, you're probably going to want to convert this into grams. So let's say you know that you need, 0.3 moles of substance A. Well, how many grams is that? So if you're converting between moles of substance A and grams of substance A, the only conversion factor that we have to do that is the molar mass of A. Molar mass of substance A. Where do you get that? From your periodic table. Okay, remember it's the same number as the atomic mass, but now when you're thinking of molar mass, you're going to express it in grams instead of atomic mass units. Okay. Now with the substance C, let's say that we want to know how many grams of substance C are going to be formed in this reaction. Not moles. We want to think of it in terms of grams, something we could actually measure on the balance. The only way that we have to relate moles of C to grams of C is the molar mass of substance C. And again, molar mass comes from your periodic table. Okay. All right, so let's go ahead and finish off with an example, a couple of examples. Okay, let's just make up some problems here. Let's say that we have, let's just go back to the same reaction we had before with the magnesium oxide. So I'm going to erase the generic here and rewrite that really quickly. It's 2 and 1 and 2. Okay, gotta have it balanced, gotta have those coefficients in there. Let's say that we want to know how many moles of magnesium oxide we can get from reacting 0.55 moles of magnesium. Okay. All right, so we're not doing this whole problem here. We're not doing the 1, 2, 3 step problem. Let's just look at what we're doing. We're trying to convert between moles of magnesium and moles of magnesium oxide. All we need to do here is a one-step problem that uses the mole ratio from our balanced chemical equation between magnesium and magnesium oxide. Okay, let's set it up. And I'll do it up here. 0.55 moles of magnesium for every 2 moles of magnesium, we're going to also get 2 moles of magnesium oxide. Moles of magnesium cancel out, you're left in moles of magnesium oxide. It's a 2 to 2, which means we're just really timesing by 1. So the answer is just 0.55 moles of magnesium oxide. Okay. Let's make it a little bit harder. Okay. Let's say that we are reacting 21.25 grams of magnesium. And we want to know how many grams of magnesium oxide are going to be formed. All right, so we're going from grams of a substance all the way to grams of a different substance. That's going to require us to go through 1, 2, 3 steps. We need to first figure out how many moles of magnesium we're talking about. Only then can you use a mole ratio and figure out how many moles of magnesium oxide that's going to form. Remember, the mole ratio is mandatory if you're talking about relating 2 different substances. Okay, you have to go through the mole ratio. That's the only way we have to quantitatively relate 2 different substances in a balanced chemical equation. Okay, and then we want our final answer in grams of magnesium oxide, so we need to use the molar mass of magnesium oxide to also figure out the final answer, grams of magnesium oxide. Okay, so let's go ahead and set this one up. So we're doing this whole flow chart. I would recommend that you keep this flow chart, the one on slide 4, handy while you're new to these kinds of problems. So maybe through problem set 8, if you're going to do the problem set 8 with me, keep that slide handy and refer back to that flow chart as needed until you get the hang of it, and eventually you won't need it anymore. Okay, all right. So 21.25 grams of magnesium. The molar mass of magnesium we got in the previous problems. We got that from the periodic table. So it was 24 point, I think it was 31. I guess I better double check. Yeah, 31 grams of magnesium for every 1 mole of magnesium. Now notice I wrote the molar mass such that grams were on the bottom. I did that because I want grams to cancel, giving me the number of moles of magnesium so that I can now use the mole ratio to figure out the moles of magnesium oxide. Okay. All right, so first step is done. You can put a check there if you want. I think I'll go ahead and do that. Use my flow chart to keep track of where I am in this problem. So now I'm using my mole ratio. It's 2 to 2, or if you want to simplify to 1 to 1, it's not going to change the math. So for every 2 moles of magnesium, you get 2 moles of magnesium oxide. A lot of my introductory chemistry students will say to me, well, it's not going to change my answer. Why can't I just skip that step? The answer is because your ratio is not always going to be 2 to 2. Sometimes it's 1 to 3. Sometimes it's 2 to 3. So it just so happens to be 2 to 2 here, which I know is going to cancel out to 1, but it's not always 2 to 2. It's not always just going to be multiplying by 1. And so sometimes it is going to change your answer. So please, please do not skip that step. Okay? All right. So we just did this step here. And now we have our answer in moles of magnesium oxide, but that's not what we're seeking. We want this expressed in grams. So we're going to do one more step using the molar mass of magnesium oxide. So for every 1 mole of magnesium oxide, remember we got the molar mass by adding the molar mass of the magnesium to the molar mass of the oxygen. And that gave us 40.31 grams per mole. Remember, good note keeping here. Label everything. Don't just write grams per mole, write grams of magnesium oxide per mole of magnesium oxide. Trust me, good note keeping can really save you on an exam. Okay, so you can go back and you can check your work. Makes it a lot easier to identify errors. So I really recommend that you have good note keeping there. Okay, grab your calculator. You are gonna need it for this. Okay, so I get 35.24. I'm going to go ahead and round to 4 digits here. Okay, so my calculator actually gave me a lot more digits than that. Grams magnesium oxide. Circle my final answer there. Okay. All right, so I don't want to overdo it with the problems here. I'm going to save that for problem set number 8. So this will conclude our tutorial number 8, and I do hope that you will consider tuning into problem set 8 so that we can work lots more of these problems together. Thank you.